Welcome to gas vapor mixtures and air conditioning. Welcome to Chapter 15, where we'll explore gas vapor mixtures and how they relate to air conditioning. This chapter connects thermodynamic principles to things you experience every day, like how your air conditioner keeps you cool or why humidity makes a day feel hotter than it actually is. We'll start by understanding the basics of gas vapor mixtures, focus on psychrometric properties, and then apply these ideas to real-world air conditioning processes. By the end of this chapter, you'll see how a few simple thermodynamic rules explain the comfort levels inside buildings and the energy consumption behind HVAC systems. Let's dive in and make this one of the most practical chapters in thermodynamics.
1. Dry and atmospheric air. Before we get into complex air conditioning processes, let's clear up something simple but essential. What exactly is in the air around us? Dry air is basically just a mix of nitrogen and oxygen, with traces of other gases, but no water vapor. Of course, what we breathe isn't always dry. Atmospheric air includes moisture, and the amount varies with weather and location. Now, to make calculations easier, we use a handy approximation. The enthalpy of dry air is just its temperature times a constant specific heat, roughly 1.005 kilojoules per kilogram per Kelvin. And for water vapor, as long as we're dealing with temperatures below 50 degrees Celsius, we can treat it like an ideal gas. This assumption keeps the math simple without losing accuracy. So, understanding these basics will make everything from psychrometrics to air conditioning a lot more intuitive. 2. Specific and relative humidity of air. Humidity plays a big role in both thermal comfort and air conditioning design. First, we have specific humidity, which tells us how much water vapor is present per unit mass of dry air. It's a simple ratio, and we use vapor pressure to calculate it. Then there's relative humidity, which most of us are familiar with from weather reports. It compares the actual moisture in the air to the maximum it could hold at that temperature. That's why on hot days, high relative humidity feels extra uncomfortable because the air is already loaded with moisture. Lastly, think about how moisture affects us. High humidity slows down our body's ability to cool through sweat evaporation. Low humidity, on the other hand, makes sweat evaporate too quickly, drying out our skin. Understanding these two humidity measures helps us design better, more comfortable air conditioning systems. 3. Dew point temperature. Let's talk about dew point temperature. It's a very practical concept in air conditioning. Dew point temperature tells us the exact point when air becomes saturated, meaning it can't hold any more water vapor. When the air cools to this temperature, condensation begins. That's why you see dew on grass in the morning or fog on your car windows. Why does this matter? Because dew point is a quick way to know if and when condensation will happen. If we cool air below its dew point, water vapor will turn into liquid water. This concept is used all the time, whether in weather forecasts or in designing cooling coils in HVAC systems. It's also easy to measure in practice. Just cool a sample of air until you see condensation start to form. That's the dew point. Simple, but super useful. 4. Adiabatic saturation and wet bulb temperatures. Let's explore two important temperatures when dealing with moist air: adiabatic saturation temperature and wet bulb temperature. The adiabatic saturation temperature is the temperature that air reaches after passing through a water-filled saturator without gaining or losing heat. Then we have the wet bulb temperature, which is easier to measure. You just use a thermometer wrapped with a wet cloth or wick. As water evaporates, it cools the thermometer, and the final steady reading is the wet bulb temperature. At normal atmospheric pressure, these two temperatures are practically the same. Why does it matter? Because by measuring the wet bulb temperature using a simple sling psychrometer, we can figure out both specific and relative humidity, making it very useful for HVAC design and weather predictions. 5. The psychrometric chart. Now it's time to introduce one of the most useful tools in air conditioning, the psychrometric chart. Think of it as a roadmap for air properties. It's a graphical tool that quickly shows you how temperature, humidity, and energy interact in the air. On this chart, you'll see dry bulb temperature on the horizontal axis and specific humidity on the vertical axis. The curved line at the far end is the saturation curve, which represents 100% relative humidity. You'll also notice downward sloping lines for constant wet bulb temperatures and parallel lines for constant enthalpy. Why do we use it? Because it's incredibly helpful for visualizing what happens during cooling, heating, humidifying, or dehumidifying processes. With just one glance, you can determine enthalpy, humidity, and dew point temperature, making the psychrometric chart an indispensable tool for HVAC design. 6. Human comfort and air conditioning. Let's connect thermodynamics to human comfort. Our goal in air conditioning isn't just to cool a room, it's to create an environment where people feel comfortable and productive. For most people, comfort is found between 22 to 27 degrees Celsius, with 40 to 60% relative humidity. Air movement also helps, ideally at around 15 meters per minute. How does our body get rid of heat? Mostly through convection and radiation, which account for up to 70% of heat loss. Evaporation takes over during physical activity, which is why sweat becomes so important during exercise. The environment plays a big role here. High humidity makes it harder for sweat to evaporate, reducing cooling efficiency. On the other hand, airflow boosts heat loss and comfort. This is why air conditioning design always balances temperature, humidity, and airflow to keep people feeling just right. 7.1. Air conditioning processes. Let's now look at the core processes used in air conditioning systems. First, we have simple heating and cooling, where the moisture content stays constant. When we heat air, its dry bulb temperature goes up, but relative humidity drops. This is why heated air often feels dry. Cooling does the opposite. Temperature drops and relative humidity increases, which can sometimes lead to condensation. Next, we have heating combined with humidification. This happens in spaces like hospitals or textile plants, where air must be both warm and moist. Air is first heated, then we add moisture using either steam or water spray. If steam is used, both temperature and humidity increase. But if we use just water spray, the evaporation process cools the air slightly while adding moisture. Understanding these processes helps us manage indoor climates to achieve both comfort and specific functional goals. 7.2. Air conditioning processes. Let's explore two more important processes in air conditioning. First is cooling with dehumidification, where air is cooled below its dew point temperature. This causes moisture in the air to condense out, which is exactly how typical air conditioners reduce indoor humidity while cooling the air. Then we have evaporative cooling, which works on a simple principle. As water evaporates, it absorbs heat from the air, lowering the temperature. However, this also increases the air's humidity. This method is commonly used in hot, dry regions. Examples include traditional desert cooling systems and devices like swamp coolers. Both of these processes are fundamental to creating comfortable indoor environments, especially in climates with extreme temperatures or humidity levels.
7.3. Air conditioning processes. Let's look at two special processes that are key in large systems. First, adiabatic mixing of air streams happens when you mix two airflows with different temperatures and humidity levels. There's no heat exchange with the surroundings, just mixing. The final condition is found using simple mass and energy balances, and interestingly, on the psychrometric chart, the final point always lies on a straight line connecting the two starting points. Next are wet cooling towers, which you've probably seen in power plants. Their main job is to reject waste heat. There are two types. Forced draft towers use fans, and natural draft towers rely on the natural rise of warm air. The process is simple. Warm water is sprayed, part of it evaporates and absorbs heat, and cooler water is then reused.
This method is crucial for efficiently removing excess heat in industrial systems.
8 key equations. Let's talk about the key equations you'll use again and again when dealing with gas-vapor mixtures and air conditioning. First, we have the enthalpy of moist air, combining the sensible heat of dry air with the latent heat from water vapor. Next, specific humidity shows how much water vapor is in the air relative to dry air mass. Relative humidity tells us how close we are to saturation, whether the air feels dry or sticky. Then comes the dew point temperature, which tells us the temperature where moisture starts condensing out. Lastly, the adiabatic saturation equation helps us calculate changes during humidification without heat exchange. These formulas are your quick access tools for solving practical HVAC problems, predicting comfort levels, and designing efficient systems. Mastering these means you can analyze most air conditioning scenarios with confidence.
9. Applications. Let's end by seeing how everything we've learned connects to real-life applications. First, HVAC systems are everywhere. Whether it's your home, car, or a factory, they all rely on gas-vapor mixtures to control comfort and air quality. Second, the psychrometric chart helps engineers quickly assess air properties during design and troubleshooting, making it an essential day-to-day tool. Third, in industrial systems, cooling tower design is critical. These towers optimize cooling in power plants and factories by efficiently removing waste heat. Finally, all of this knowledge feeds into human comfort analysis, designing indoor environments that are pleasant to live and work in across different climates. By mastering these concepts, you're better equipped to solve real engineering problems.